Next slide. Our next question, how to reduce this number? Yeah. So, how to reduce? Yeah. So for this class, our biggest concern, biggest problem we want to solve, we want to improve the overall performance. Okay. Yeah. Improvement. Choose a strategy. Now we are not satisfied. If someone told you the previous algorithm is a really bad one, very bad, not acceptable, if your customer complain a lot, suppose, so you deliver this program to your customer. So after they use to solve a business problem, couldn't earn a lot of profit. Okay, yeah. So too slow. So not much profit. Okay. They lose money. They're using your program but lose money. Okay. So they give you feedback. You need to improve performance. You need to improve the performance more than 10 times. You need to reduce the number of, the response time, 10 to 1. You need to use 1/10 of the response time to do the same thing. Otherwise, I cannot earn any money. Okay? Let's assume that's that background. Okay? So give you pressure to improve it. Otherwise, you cannot win any business. Okay? Your algorithm is too slow. Okay? Yeah. Yeah. Let's use that, superficial story. Yeah. All right. Cost ratio 10 to 1. Right? When we do improvement, which part we should spend our time on? Multiplication. Yeah. Bottleneck. We want to spend our effort on multiplications. So our goal, we want to reduce the number of multiplications. Okay? Yeah. The strategy, now you have the strategy. Reduce the number of multiplications. Right? You see, we can easily find the right strategy here. That's our strategy. Okay? You need it. But now you can see, for this problem, finding the right strategy is not that hard, but execution is hard, right? How do you do it? Execution is hard. Okay? Yeah. Execution. But for some other problems, even finding the right strategy is hard. Many other problems, you don't know what's the strategy to use. Yeah. All right, so another case here. Even with the cost, well, so here, our strategy. So because when you do when you try to reduce number of multiplications, your method could increase the number of additions a little bit. So you need to sacrifice on some other parts of the computation. That's fine, because we gain big, but we lose a fraction of it. So that's fine, right? So it's okay, trade-off, right? So we can do, do that kind of adjustment. Yeah. But for this problem, actually, we do not increase additions. Okay? We still do the same number of additions. All right. All right. So this is the starting point. We compare. We try to improve. Okay? Yeah. I just said 10 to 1 ratio, right? Remember, your customer complained. The customer set a goal for you. You need to achieve at least 1/10 of the response time. Okay? Otherwise, you lose money. Okay? You lose business. Okay? All right. Here, we try to reduce this part. Okay? Not that part. Okay? Yeah. Huge part. Okay? Not that part. Okay? Yeah. All right. Okay, yeah. Another strategy. Yeah, yeah, because after the first step, our second step, we need another strategy, right? So we may need many strategies. Okay? Yeah. If one step is very hard, usually we need some special strategy. Okay. All right. Because the strategy usually tells us what direction to go. Okay? If you don't have strategy, do you know how to solve? You have no direction. Right? I don't know. So, where do I spend my time? Yeah, because I don't have strategy. Okay? Yeah. All right. Yeah. Execution. Yeah. Suppose you know the direction. Yeah. I know I need to go along that direction. Okay? Yeah. So execution tells you how to get there. Right? Yeah. You still need to, fix a lot of details. Yeah. Try to reach there. Okay? So you see your goal. There is a light, it's there. Okay? But how to get there? Okay? There is a lake in the middle, so you need to find a path, right? Yeah. Yeah. Things like that. Okay. A question: how to reduce the number of multiplications? Yeah. But you need to find the reason to reduce number of multiplications. Which factor causes us to spend that many multiplications, right? You need to find that. Otherwise, how do you reduce? You need to find the problem. Where is the problem? So then you can fix that problem. Okay. Yeah. Diagnose. You need to find it. Okay. All right. So let's find that problem. Okay. Multiplication reduction. Okay. Another strategy. Yeah. Yeah. So here you can see strategy by strategy. Yeah. Yeah. For this class, you will see, you will learn dozens of strategies. Okay. Hope. So after this class, you can use those strategies to solve real-world problems. Because most of those strategies very general. Okay? That means you can apply to many general problems. Okay? Yeah. You will see. Yeah. This strategy, study a simpler case. This is a commonly used method. Although it's so simple, it is so simple, but very effective. Very effective. Study a simpler case. After we study some simpler case, we get an idea. We find the problem. We get an idea. Okay? So, what is the simpler problem? Smaller data size. Yeah. When this number is small, that's easy, right? N is not a big one. 2, 3, 4, is that easy? Right? Yeah. Simpler problem with smaller problem size. Okay? Yeah. Simpler. Yeah. So let's do that. Let's consider n equals 2. That should be easy, right? Yeah. 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 So we can solve that easily. Okay? Yeah. How do we do this? Okay? Yeah. So now, this is a quadratic polynomial. To evaluate this quadratic polynomial, we have a lot of confidence. Right? Only 3 terms. We have a lot of confidence. We can do a lot of things on it. Yeah. Okay. All right. But how to do it? Still not that obvious. Okay? Still not that obvious, even for quadratic polynomial. But if I point one critical thing out, you will realize, wow, you can do like this. You can do things like this. So that's why the thinking is so important. The thinking is so powerful. Okay? If you can see the main point, you see the solution. Okay? All right, let's see. Let's look at the property. Let's try to explore the property of these 2 terms. Some property. Yeah. The property is important. We need to really know the property of our data. Okay. Can you see any property there? Just focus on those two terms. Can you find any property there? Good. That's a good one. Factor. Or let me, say in a different way. We can factor one common factor, right? There is a common factor. Do you see the common factor? Yeah. Common factor x. We can take that common factor out. Okay? All right, so now another common method we use to solve problems called a transform of the problem. Okay. Many times, in order to look at the problem in a different view, we need to transform the form of the original problem so that we can see the problem differently, in a different view. When we use a different view, we can see better structure. We can get an insight of the problem. Insight. Okay? Find the insight. Okay? All right. Change the structure for new outcome. If you do not change structure, you cannot get a new outcome. Okay? So sometimes, or frequently, we need to change the structure of the original problem. So that's what we call a transform the problem. Okay? So we frequently need to do that for this class. Factorization. How do you do transformation? Factorization. The technique, factorization. But here, this technique is trivial, right? Do factorization, this step is trivial. Okay? So let's do it. Factor that common factor out. Okay? Can you see something new after this transform? Can you find some new property? All right, yeah. Make it simple. Let me just point that simple thing out. Let's count the number of multiplications after this form change. These two formulas are exactly the same, but they have different form, right? Different forms. Let's count the number of multiplications in the second expression. You have 1 here, you have 1 here, right? So you have 2 multiplications, right? But how many multiplications do you have here? Okay? 3, right? 2 here, 3 there. The same result, the same number, but you just change the form, you get different number of multiplications. Is that good? Is that what we need? Okay? We reduce the number of multiplications. We use a simple case. We can see this easily. Our gain is 3 to 1. The original multiplication 3, we cut it and get 2. Is that good? So is this a good solution? Okay? Yeah. So now you see the point. So now you get an idea for this class. That's what we need to do for this class. Okay? This is the manipulation. Here, we need our creativity, right? Because to find things like this, it's not easy. We need our creativity. We need powerful thinking here at this step. The result is great. From 3 to 2. But that's for the small example. How about for big example? When you have a lot of terms, how many multiplications you can reduce? So think about that. Can you reach your customer's goal, let's say, 1/10 of the fraction of time? It's possible, right? It's possible. Yeah. So think about that. Okay? All right, so we run out of time. Yeah. So let's stop here. So next time. So we continue. Yeah. Yeah, just a minute. Let me stop the video. Relatively hard to solve. So there is one commonly used strategy. Consider a simpler case. So we consider the case when n equals 2. By examining a special property, because there is a common factor between the last two terms. So we use the factorization technique, a simple technique. So we transform the expression, we change its form in this way. After that, we count the number of multiplications. One here, one there, and we get the result, 2 multiplications. If we compare with the older way we need 3. So last time one student asked me why you get 3. Right? So here, let me explain that. 1 multiplication here. Okay? Another one here, x squared, you need x times x. Okay? 2 multiplication here. So total 3. Yeah. Our gain, we reduced multiplication from 3 to 2. That's what we did last time. Okay? Yeah. Now let's continue this story. We want to generalize this simple technique to arbitrary n. Arbitrary n case. Okay? Yeah. So how to generalize it? We generalize the reduction. Multiplication reduction, right? Multiplication reduction idea. Okay. We try to get something. Yeah. After we try this simple example, we try to summarize some rule so we can apply to the general case. So what is the rule? Common factor. Yeah, we already discussed about that. So the key here is the factorization. Okay? So here we have this idea. If we can do this factorization for the general case, then we should have pretty good chance. Okay? Yeah. So the question is, how do we apply factorization to the general case? Okay? So here, another strategy. Yeah. Strategy for generalization. Yeah. So this time, we use this strategy. Do factorization as much as we can. So, as much as we can. Okay? When you have a chance, you try to maximize the way you do the factorization. Okay? So here, actually, there is a very simple but useful method we used here, greedy idea. So later we will learn greedy algorithm. So here, the first time we use this greedy idea. As much as we can, that means, in our description, it's a greedy behavior, right? Greedy. So here, we try to do things in a greedy way, as much as we can. Okay? All right. So how do we do as much as we can? Okay? First, the first factorization we want to apply on the maximum number of terms. If we cover the first term, then we have a common factor, right? So we do factorization. Okay. All right. After we do complete the first factorization, we cover the first term, then we can do factorization on the remaining terms, and so on. Okay. So here you can see, if you maximize the way to do the factorization, you can take advantage of the gain we enjoy in the previous example. So that's the simple idea. Yeah. After this transformation, this is a nice transformation. After this transformation, now let's count the number of multiplications we need for this calculation. How many? Right? Here you can see we use counting quite a lot. Okay? The counting, we still use our old counting technique. So can you? The counting technique we did last time. Count by reference, right? The first multiplication, can we associate with some reference, some easy, nice reference? Okay? Let's associate this multiplication with A1. How about that? A1. A1, we use A1 as reference. Okay? The second multiplication associated with A2. Right? That's the reference. Okay? Yeah, 1-to-1 correspondence. One multiplication corresponds to AI, A sub I, okay? A something, right? So then this multiplication, the last one associated with AN. So how many multiplications do we have? How many A's do we have? N. So that's the easy answer, counting by reference. Okay? Yeah. Very effective. Okay. Answer N. Now, conclusion. Yeah. So, how much do we gain in this method? Yeah. Multiplication reduction. Let's compare. Okay. The old technique, old method, we have this number, this expression from last time. The new one, N. Can you see the improvement? How much is the improvement? Here you see two formulas. Definitely you know this expression is much smaller than that one. But do you have an idea how much smaller? Okay, we want to get some, feel about this improvement. How much we want to feel about it. Okay? So let me try a few numbers. First number, when n equals 1,000. Let's compare these two numbers when n equals 1,000. The first expression, let's plug in 1,000, we get 500,000. So the improvement is from 500,000 to 1,000. Okay? That's the 500 to 1 ratio. Remember the story I used the last time? I said, your customers want to cut the cost to 1/10, right? Ask you to reduce the cost 1/10 of the old solution. Here, you can see we reduce 500, much larger than 1/10. See, much larger than 1/10. 1 over 500. That fraction. Let's try another one. When n equals a large number, 1 million, then we plug in into the first formula, we get, what's this number? So many zeros. 500, not trillion yet, 500 billion, right? 500 billion, that's the number. Versus, 1 million. So the ratio is 500,000 to 1 ratio. That big, 500,000 to 1. Okay? Here, although when you see this number, that's a big difference. I want you to feel in another way. Okay? So try to use our everyday life to see this huge difference. How do I compare in this way? 500,000 to 1 ratio. 1. Let's use the simple time unit second. All right? A second. So we know how long is a second, right? Yeah. Suppose we use our second method. We can calculate this polynomial, the polynomial with 1 million terms, or with n equals 1 million, not 1 million terms. Degree 1 million, right? Degree 1 million, okay? If we use our efficient algorithm, it's 1 second. If we use the old method, that's 500,000 seconds. How long is 500,000 seconds? Okay? So let me convert it to days. How many days do we need? 5.8 days. 5.8 days approximately versus 1 second. Okay? Now you can get the big difference. Right? If you use the new method, 1 second, you get a result. If you use the old method, you do the same computation, but you need to wait 5.8 days to get a result. 5.8 days. So this example, you see the power of the algorithm. Why the difference is huge like this? Because of the efficiency of the algorithm. Okay? Yeah. That's what you want to learn for this class. You want to improve your algorithm like this. Okay? Yeah. All right. Yeah. Any question about our first example? Yeah. Problem number 1. Okay. And this smart algorithm, we call it Horner's rule. That's a famous rule. Horner's rule. Okay. Yeah. I mentioned last time in section 6.5, chapter 6, 6.5. Yeah. Yeah. Because I feel it is the right place to talk about this, so I put it here. Yeah. All right.